Hi everyone. So I just wanted to make a follow-up lecture to what we finished off today talking about. So we stopped last time talking about having a base dissociation constant. So that was our Kb, which was, we related that to being Ka. So what we're going to spend for the next part of this lecture is relating this idea of the acid dissociation constant Ka to that of its conjugate base and its Kb value. So what you see here is we have a chart of different compounds that act as bases. So we start with ammonia, and this is the most common, I guess, Gen Chem weak base that we deal with, so the NH3. So we see we have a Kb of 1.8 times 10 to the negative fifth. A relatively strong Kb, so we know ammonia is a relatively strong weak base, right? And the way we talk about weak bases is that they're not necessarily weak in their sense to do chemistry, but they're just weak compared to very strong bases, say like sodium hydroxide. Because you definitely don't want to be sticking your finger into a bottle of concentrated ammonia. You'll have a bad day on that one, despite the Kb being 10 to the negative fifth. The the conjugate acid, though, of ammonia, which is the protonated form of NH3, which is NH4 plus, has a Ka of 5.6 times 10 to the 10th. So we have this back and forth. So we know we could have NH3 react with water to form ammonium and hydroxide, but there can also be the reverse reaction of that ammonium reacting with the hydroxide to go back towards NH3, and that's going to be described by the Ka. And we're going to see that there's actually a relationship between, I can't get this thing to, oh, I guess we have no pointer for this lecture, I guess, so it's all going to be through voice. So what I'm trying to point at is the Kb value of ammonia, which is 1.8 times 10 to the negative fifth. We're going to see its relationship to its Ka of 5.6 times 10 to the 10th, 10 to the negative 10th. So what is this relationship between the acid dissociation constant Ka and the base dissociation constant Kb? So we have this acid reaction, the acid reaction with water, where the ammonium, so the protonated form of ammonia, so it acts as an acid, can donate a hydrogen to the water, so it acts as a Lewis acid that transforms water into into hydronium, which is a H3O plus, and the ammonium is converted to ammonia. So we have that reaction that's in equilibrium, and we also have the reverse reaction, which we have ammonia can accept a proton from water, in which it becomes ammonium and produces the hydroxide anion, and that's described by that relationship of Kb. So we realize that they're just the mirror image of each other, right? So we got to think, so what is that relationship between Ka of a weak acid and the Kb of its conjugate base? If we add this all together and actually take into account by crossing out anything that appears on both sides of the reaction, so in this case ammonium is on both sides of the reaction, ammonia are on both sides of the reaction, we have something that we're familiar with, something we've talked about a couple weeks ago, or a week ago, in which water reacts itself to form hydronium and hydroxide, right? That being the Kw, which is this autoionization of water. So what we see by looking at our mathematical laws is that Ka times Kb, so Ka being products over reactants, so hydronium times ammonia over ammonium, and we multiply it by the Kb, which is ammonium times hydroxide over ammonia. Let's see what crosses out. Well, there's my ammonia that crossed out. There's my ammonium that crossed out. Guess what? I'm left with the same exact expression, that the concentration of hydronium times the concentration of hydroxide equals the autoionization constant of water, or Kw. So for a conjugate acid conjugate base pair, the Ka multiplied by the Kb is always equal to Kw. And that's what we see here. We have the Ka times the Kb. We get back to what we expected, Kw of 1 times 10 to the negative 14th. So this is just a little bit more of the math summarized together. I'll let you guys take a look at that and mull it over from the slides, but it's basically applying everything that we learned in the first lecture about strong acids and strong bases to what we're learning now about the Ka and Kb of weak acids and weak bases. So we have our first problem to go through. So like we did in class, we did a bunch of these. This problem is asking us to calculate the pH of a solution. So remember pH being the negative log of the concentration of hydronium of a solution of 0.40 molar ammonia solution. It's at 25 degrees C, and we're given the Ka for ammonium, which is the conjugate acid of ammonia, is 5.6 times 10 to the negative 10th. And this is what's given to us. It gives us the base reaction. So that's the first thing to recognize. What direction are we looking at? We are given ammonia plus water yields ammonium plus hydroxide. So we know we're actually looking at the base reaction. If we set this up, we have our ice table. We know what our initial concentration of ammonia is. We're going to say the concentration of ammonium is 0, right? Because there's no other source of it. And again, we're approximating the concentration of hydroxide to be 0, but in actuality it's 10 to the negative 7th due to the autoionization of water. But because that is such a small number, we're going to just essentially call it 0. We take a look at our change row. We see that we have minus x on the reactant sides and 2 plus x's on the product side. And we end up with our equilibrium concentration expressed as a function of x. If we put all of that together, we'd be looking at Kb, but we're given Ka. So we're left with this dilemma. Okay, all the information I have inside my ice table is for Kb, but I'm given Ka. Well, what we can realize is that there's a relationship between Ka and Kb. All I have to do is solve for Kb because I know the Ka because it was given to me in the problem. Kw is essentially, for us, we'll consider a constant, though it technically is just at 25 degrees Celsius. We know K differs with temperature, but we're going to do everything at 25. We rearrange the equation. We solve for Kb. We got 1.8 times 10 to the negative 5th. Now we can go ahead and use our ice table and solve for x. So there's our Kb expression. We have a numerical value for Kb. We can start to plug things in. So let's do that. Now we have our Kb expression using our equilibrium concentrations that are expressed as a function of x. We can make our first assumption. Again, you have the option of just directly plugging it into the quadratic equation. But we're making our assumption that x is much, much, much smaller than the concentration of ammonia. We can check that assumption, that 0.0027. If you plug that in and check the percent of 0.4, you're going to find that it accepts our assumption. It's very small compared to 0.4, so we're good to go ahead. And what we can do now is start to solve for the hydronium concentration, right? So again, this is what we kind of tried to hammer home, and we had a pretty long conversation about when using the ice table in terms of Kb, we need to recognize what x is solving for. Because we started with the base reaction, x represents the hydroxide concentration. We have several ways to go about it. We did it one way in class. This is another way to go about it. Before, we used the pKw, the pH, and the pOH. And the way that I've chosen to written out the slides, instead of using the P of all of those, I'm just using the Kw expression directly. So we know what Kw is, which is 1 times 10 to the negative 14th. We know what the concentration of hydroxide is, because that is X, and it's 0.0027 molar. That leaves us only with hydronium concentration left to solve for. We rearrange the expression, and we can solve directly for the concentration of hydronium. We plug that into our pH definition, which is the negative log concentration of hydronium, and we end up with a pH of 11.43. And as always, we ask ourselves, does that make sense? Yes, it does. We're dealing with a weak base, which is ammonia, which means we should be somewhere in the vicinity of, say, not 14 or 13, because that's a strong base, but you're talking about, all right, 12, somewhere down to 8. For being a weak base. That's our general, rough estimate. But as long as we're below a strong base, which is 14, and neutral, which is 7. So that makes sense to me. So that's going to end what we're talking about in terms directly of dissolving something that behaves as an acid and behaves as a base when dissolved in water. This was something that I didn't realize was happening when I was doing scientific experiments to actually, I mean, I knew of it, but it's funny that when you finally get to grad school and start running your own experiments, I didn't even take into consideration that when you dissolve salts that aren't necessarily bases, they can actually affect the pH. And so it's funny in hindsight, I'm like, oh wow, that makes so much sense. But what I want to do now is attack it early and figure out, okay, why when I dissolve something like iron chloride, why does that end up being an acidic solution? So we can actually change the pH of a solution by dissolving salts and not necessarily something that is just straight up, okay, I can pull it off the shelf and say it's an acid, or pull it off the shelf and say it's a base. So we have a couple of rules. So I'm going to just read through them a little bit slowly and then try to describe what's happening. So it's saying that salts that yield neutral solutions. Okay, the first one you think about is sodium chloride. Well, you drink it and yeah, it's salt water and you can taste it, but if in low concentrations, it's just salt water, right? It's what you cook your spaghetti in. It's not burning your esophagus or anything. So let's follow some of these rules. And it says the following ions do not react appreciably, so it means not a lot, with water to produce either hydronium or hydroxide. So it's basically leaving it neutral. What it's saying is cations from strong bases, so that would be something like lithium, sodium, potassium, because those strong bases would be lithium hydroxide, sodium hydroxide, and potassium hydroxide. And then also the alkaline earth metals, which are just the second column, which would be magnesium 2+, calcium 2+, strontium, and barium. The only exception is beryllium. We're not going to go too much into that. That's based off of molecular orbitals. But for the most part, the reason for this is that if you think about sodium, so we'll take sodium hydroxide, the Na plus as our example. When you add that into water, it's basically what it's in the form of sodium hydroxide. It doesn't want that hydroxide so much that it's just giving off freely into solution, right? It goes freely into solution. That means that sodium plus has no real affinity for hydroxide, so it's not trying to pull it out of the water solution. Essentially, it's just a spectator. So it's not going to have an effect one way or the other on the equilibrium of hydronium or hydroxide. And the same thing goes for the anions of strong monoprotic acids. So again, Cl-, Br-, I-, NO3-, right? All of those would have been hydrochloric acid, hydrobromic acid, hydroiodic acid, and nitric acid, all very strong acids. Same thing with the chlorate anion. Those are all strong acids. So again, if you just have chloride floating around, it has no real affinity to try and attract an H to it because it's such a strong acid. If it did take an H, we already know that Ka is about 1,000,000. It's immediately going to give that H back up to water and make hydronium again. So there's, again, no real impetus to affect the natural ionization constant of water. So you still have that concentration of 10 to the -7th for both hydroxide and hydronium. So that's our first rule. Summarize, cations from strong bases and anions from strong monoprotic acids do not affect the pH of a solution. So what happens, though, when some salts do affect the pH of a solution? So we'll read through the slide. Salts such as ammonium chloride are derived from a weak base, so there's your NH3, and a strong acid, HCl. Right? So if we visualize that chemical reaction, there's our ammonium plus water to make hydronium plus ammonia. Right? So the ammonium cation is the conjugate acid of the weak base ammonia, while chloride, Cl-, is neither acidic nor basic. So we take that into consideration. We have that NH4 and Cl-. Our last rule told us the chloride is not affecting the hydronium concentration, but the presence of having a weak acid in the form of ammonium, well, we know ammonium can also donate that H to water to form hydronium. And so what this actually does is when you dissolve a compound like ammonium chloride, you're actually pushing the equilibrium towards forming hydroxide, and it makes an acidic solution. Right? So you have basically a source of hydrogen, it donates it to water, forms hydronium. You've now perturbed the equilibrium between hydroxide and hydronium and made more hydronium. So you have an acidic solution. So what happens, though, when you dissolve something that has a weak base and a strong, a weak acid with a strong base cation. So if you have a salt like sodium cyanide, right? What it's saying is when this dissociates, you have the strong Na+, right? That was associated with sodium hydroxide. Again, it does not have any real affinity for the hydroxide in the solution, has no effect on that hydroxide-hydronium balance. Cyanide, however, can react with water and accept one of the hydrogens from water. What this ends up doing is disturbing the balance between that hydroxide and hydronium of pure water. It took some of the hydrogen from the pure water. So that means you're now going to have an excess of hydroxide. And so by dissolving the sodium cyanide, you actually create a basic solution. So I know it's a little bit weird to be thinking about that, but you actually have seen this when you did it in lab. This is during Le Chatelier's principal lab, where you started with acetic acid, which is CH3COOH, and then you also added sodium acetate, which was actually the same idea what we have here, where we have the cyanide, where there's no H involved connected to the cyanide. Instead, it's a metal cation. The same thing happens with the sodium acetate. The acetate has no additional H to give. It's counteracted by having that sodium. When it dissociates, what it's going to do is pull H's towards itself. And so that ends up causing the solution to become more basic. So we have this question though, so let's do a little example. All right, so it says the pH of an ammonium carbonate solution. All right, so now I've got a combination. If I break that down, ammonium, well, that's the conjugate acid of a weak base, which makes it a weak acid. Carbonate is the conjugate base of a weak acid, carbonic acid. So what am I going to do? Before, every other example we had was a strong acid with a weak base, or a strong base with a weak acid. But now they're both weak. So how am I going to approach this? So is it acidic or is it basic? Right? So we need to break this down. Essentially what it comes down to is realizing ammonium, right? What is its Ka? And carbonate, what is its Kb? And we're going to compare the relative order of magnitude of both of them. So in the case if you have a Ka of your weak acid is greater than the Kb of the weak base anion, then you're going to have an excess of hydronium. Because the Ka dominates, we push more towards having hydronium. pH drops below 7. Ka is less than Kb, so that means the Kb of, say, carbonate was bigger than ammonium, the Ka of ammonium. Well, then we're going to have an excess of hydroxide, so we end up with a pH greater than 7. When they're approximately equal, right, it basically doesn't affect the pH at all, and you get a pH approximately of 7. So actually, let's look directly at this ammonium carbonate. So we have the Ka for the forward reaction of ammonium reacted with water. We get a Ka of 5.6 times 10 to the negative 10th. Well, that's a really small number. That means ammonium is a really poor base compared to, a really poor acid compared to ammonia as a base. The Kb for carbonate is actually pretty large, right? We end up with 1.8 times 10 to the negative 4th. So that means that the carbonate is more basic than the hydronium is acidic, and so you end up with an acidic solution because the Ka is less than the Kb of carbonate. And so what I want to do, we'll finish this up now. Instead of quantitatively, we're going to be looking at qualitatively of what affects the strength of acids, and you'll be doing this a lot more in organic chemistry. What we want to do now is just kind of have a general idea of what's going on. We can talk more about what's happening on a molecular level and a microscopic level when you get to orgo, but right now we're just going to get in general trends. So what we notice about acid strength is actually going to go up as the electronegativity between the hydrogen and its conjugate base. So in this case, all of these are halogens, right? As that HA strength goes down. What that's saying is because if you have a high HA bond strength, right? So it basically says the bond enthalpy between HF is very strong compared to something like HI, which is a little bit weaker, right? That means it doesn't take very much energy to break the HI bond, but it takes a lot more to break the HF bond. And we're going to find that this also trends with electronegativity. So as electronegativity goes up, right, the acid strength is also going to go up. And that makes sense, right? So something like when you have CH4, which is methane, it's basically saying it's a non-acid. Methane is not acidic. You have basically equal sharing of the bonding electrons, so it's a pretty low electronegativity difference between the carbon and the hydrogen. Very low acid. As you start to go up in terms of electronegativity, as that polarity of that bond increases more and more, it makes it a lot easier to break that hydrogen off to release it and form hydronium when dissolved in water. And so it's exactly what we see. We go from C to N to O to F. If you notice, that's literally going across the periodic table. And as we go across that row, we notice that the acid strength increases. The last bit we're going to talk about is oxoacids. So oxoacids are literally acids in which the proton that gets donated is attached to an oxygen. So oxoacids. You'll notice on the left-hand side of the screen, it says we're talking about the Ka. Okay, so that's what we're describing. Those are our numbers. And then we look at it says the electronegativity of Y. Y just means the other part of the molecule that's attached to the O, that's not the H. So in the first example, that would be I, then Br, and Cl minus. So what we're noticing is the electronegativity of I as that increases. So now if we looked at a periodic table, we're actually going up one of the columns, the halogen column, I to Br to Cl, Cl being the highest. That's increasing our electronegativity. And what it ends up doing, so if we look, let's take a look at the first one, the HOI, because it's basically the same structure for all of them. The oxygen is pretty electronegative. So if we just look at the HO bond, it's already polar and it's partial negative on the oxygen. So we're pulling that electron density away from the hydrogen. We're also connected to something that's also electronegative through a bond. And what that I is doing is pulling even more electron density towards the right-hand side of that molecule, weakening that bond between the O and the H, making it easier to donate to another molecule, making it a stronger acid. So as that electronegativity of the element Y increases, like in our case bromine up to chlorine, we see that pull all to the right-hand side of the molecule increases, further weakening that bond to the H, and we notice that our Ka starts to get less and less, or rather it gets larger and larger. Right, to the point where we have HOCl is more acidic than HOI. And the same idea applies. So we have our oxoacid, so the H and the O, and what we find out is that as we attach more and more electron withdrawing groups, you're going to get more and more and more acidic. So we look on the left-hand side here, we have HOCl. So we have the O and the Cl pulling away electron density from the H, making it easier to dissociate. Now we have OClO. All of that is pulling really hard to the right, so the H is weakened more. Again, we add more O's. Oxygen are really good at pulling away electron density. So as you add more and more and more oxygen to that Y group, you're pulling more and more electron density away from that H. And we'll talk a little bit more later. I don't know if I'm going to get into it, but the stability of the conjugate base. But as more and more oxygen get attached to that Y group, basically it becomes that electron wave function becomes so large. It's actually such low energy. It's pretty stable. When it gives up that H, it has no reason to take it back. It's actually pretty stable to be an anion. But take-home message is, as we add more and more oxygen to that Y group, that electron withdrawing group, it becomes a stronger and stronger acid. And so basically, this is what that chart summarizes. You can see as we start adding more and more electron withdrawing groups, we end up getting more and more stable and become stronger and stronger acids. The last thing we want to talk about is basically our last definition of what an acid is. So we've had the Arrhenius definition. we've had our Bronsted-Lowry acid definition, and we're going to add our last definition, which basically encompasses, this is our broadest definition, which describes all acids and all base reactions. Right? We're going to find out this expands beyond just proton donation, but we'll start with proton donation and proton acceptance. So Lewis acid, so this is our most broadest definition, is just an electron pair acceptor. A Lewis base is electron pair donor. So nothing's connected to hydrogen at all in this case. But if we look at the reaction of a proton with ammonia, we see that the lone pair on the ammonia can attack the hydrogen. So now we have a lone pair donor, which is our ammonia. So all Lewis bases have lone pairs. It donates it to the H+. The H+ accepts it. So the H in this case is our Lewis acid, which is our traditional definition of an acid. And our Lewis base is the one that donated the pair of electrons and accepted the hydrogen. So in this case, when we're looking at a straight up acidic proton plus a base, it's both a Lewis acid, a Lewis base reaction, and also a Bronsted-Lowry acid, Bronsted-Lowry base reaction. So again, we look at this. This is just more of a fancy view. But you'll notice that in between part there with those arrows that are moving around, this is called a reaction mechanism. It's showing the flow of electrons. For right now in 1102, we're not too concerned about the flow of electrons, but this is something you will definitely see in Orgo. But what I really wanted to show was, we see up here a Lewis acid Lewis base reaction. If we look up there, there's no source of hydrogen at all, because that those NH bonds that are in ammonia, those are pretty stable. Those are not acidic bonds. What we see instead is that we have a lone pair on the nitrogen that attacks the Lewis acid, in this case with the copper. So we have our lone pair donor. Well, there's our Lewis base. We have a lone pair acceptor of copper. There's our Lewis acid. This is a acid-base reaction, or particularly a Lewis acid Lewis base reaction, but there is no transfer of hydrogens or hydroxides at all. So this is our broadest definition of an acid-base reaction, and that's where we're going to stop for this, and that will conclude the chapter. And so we'll pick up next time, continuing up with the syllabus as it dictates that we need to finish for the rest of the course. So I will see you all on Wednesday. Enjoy the long weekend, and study up for that quiz. If you have any questions, shoot me an email, and I will get back to you as soon as I can.